Okay, so hello everyone. My name is Annie, and for the Simulink Student Challenge 2023, my topic is going to be Quantum Cryptography Simulator. To give a preview of quantum computers are devices that involves properties of quantum mechanics to enhance computation. Quantum computer incorporates quantum theories and the uncertainty principle, quantum entanglement, etc. Quantum computers uses qubits as the basic unit of information as compared to classical computers that uses binary codes as 0 and 1. So by firing some microwave subatomic particles at these qubits, we can control their behavior, change their direction, read out individual values of quantum information. If we talk about cryptography, it basically is a process of hiding or coding information such that only a person that is intended to read it can read it. Quantum cryptography is a method of encryption that uses quantum mechanics to protect data in quantum computers. It's also called quantum encryption. Quantum cryptography makes it impossible for hackers to access data. It is a very powerful encryption system, and even if a hacker has their own quantum computer, it cannot break the code and not trigger the messengers that their information has been tampered with. So it's a newer and safer way to encrypt information. And the best known example for quantum cryptography is the quantum key distribution method. The quantum key distribution method has a BB84 protocol that is the most famous protocol used in quantum cryptography. It was invented in 1984 by the scientists, and this protocol is basically based on Heisenberg's uncertainty principle. So it's the most prominent quantum protocols, and all the other protocols are based as variants of the BB84 protocol. So in BB84 protocol, there are two messengers that can transmit their messages as random key secrets by sending a string of qubits or photons with the private key encoded in their polarization. Uh, uh, we are going to discuss the third party involvement in quantum cryptography in the later slides. So the protocol basically uses four polarization states as horizontal, vertical, diagonal, and anti-diagonal states. Let us take an example for this BB84 protocol. Let us say there are two messengers as Alice and Bob, and Alice wants to send in data as 101101 to Bob, and she is going to use a quantum cryptography to generate to transmit this data. So the most important feature here is this filter we're gonna use. We're gonna use two filters as addition filter and multiplication filter. That basically says that it's a rule that if we get the unit 1, the addition filter is gonna give us a vertical vector, and the 0 unit by addition filter will give us a horizontal vector. In multiplication filter, the value 1 is gonna be as the anti-diagonal, and the value 0 is gonna be the diagonal. So if we use this filter in this example, we are gonna get okay, we are also gonna reorder the vector as we like. So if we're using as the addition, multiplication, addition, multiplication, addition, multiplication. So for the unit 1 with the addition filter, it's gonna give us a horizontal vector. For the 0 unit with the multiplication vector, it's gonna give us a anti-diagonal vector. For 1 with addition filter, it's gonna give us a vertical vector. with the unit 1 with multiplication filter, it's gonna give us a diagonal. With 0 unit with addition, it's gonna give us a horizontal vector. With 1 multiplication filter, it's gonna give us a diagonal vector. Now this encryption is gonna be transferred to Bob. Now Bob doesn't know what this order of filter we have used here. So he's gonna use a trial and error method approach. He's gonna use all the addition filters to get out a data. So when he uses this addition filter for the horizontal vertical vector, it's gonna give us as 1, the diagonal as 0, vertical as 1, anti-diagonal as 0, horizontal as 0, anti-diagonal as 0. So it clearly we can say that the original data doesn't match entirely with the data generated by Bob, but some of it as does match. So as 1, 1, 0, 0, 1, 1 and 0, 0 matches the original data. So we're going to use this 4 data as quantum key to configure which type of filter is actually being used here. So this is the example we're going to use in our quantum cryptography simulator. Basically, the simulator is creating an environment how encryption would occur in a quantum computer. And in the simulation model, instead of polarization detectors, we are replacing them with some condition statements that determine the direction values of the qubits. So each of these unit present here convert individual units to quantum signals to be sent to receiver, that is Bob. So these quantum signals are received and then some trial and error method we choose between some filters to be converted to original data. These trial and error method gives us the quantum key. So when we use the same Alice and Bob example in our simulation, let's suppose Alice assigns qubit as 101101. These qubits are then taken to this if and else condition, which is used as filter in our simulation. So we have used two types of filters here. First one is returning horizontal and vector values as we discussed in the addition filter. Here we are assigning horizontal as 3 and vertical as 4. Same as in the multiplication vector, which return diagonal and anti-diagonal values, we assign them as 5 and 6. These are the if and else conditions that we have used in the two filters. So, for understanding the working of a single unit present in our simulation, when Alice gives out this information to the filter and the filter processes it and gives us, let's take for an example 3, which is the horizontal vector. These 3 is taken by the system of Bob, and Bob's system is going to use some trial and error approach to configure which filter was being used in Alice's system. So when Bob uses this trial and error approach, he's going to get two types of data as he's getting 0 and 1. Uh, so we're going to match this data with the original data, and we're going to choose between these filters in the switch, which matches the original data, as this one's matching the original data and it's giving out 1. So the output given by the filters which are matched correctly are used as quantum key. The quantum key determines the order of the filter and then reorders the condition to produce original output. If we talked about the third person involvement in quantum cryptography, quantum computers basically use polarization detectors to know the direction of subatomic particles. But with this process of detecting the direction of subatomic particle, it actually changes the original data. So if these data had to be sent to other people, they will receive a very different set of values. This process of quantum cryptography ensures that no third person shares the information. So if a third person even tries to get the information, the original message will be changed and the original messengers know that the data had been tampered with. So this basically uh, doesn't involve any person involvement in their information. Some of the limitations for this quantum simulator is that this model doesn't include the restriction of the third party involvement in it. And there are newer and more precise protocols being developed for quantum cryptography right now. Uh, so I guess that's it. Thank you for Simulink for giving me this opportunity to present my project, and I had a lot of fun making it. Thank you.